So good morning and welcome back. Today we'll turn to differentiable manifolds, and we pass from topological manifolds to differentiable manifolds by actually removing charts from a topological atlas. So that's the first step, 4.1, adding structure by refining the maximal topological atlas, or the maximal C0 atlas. So we saw before that if we have a topological manifold, so MO topological manifold, that we can actually construct an atlas for this manifold, and there is only one maximal topological atlas, because all the charts you can choose are automatically, by virtue of the definition of a topological manifold, C0 compatible. It was a fully redundant notion, an atlas was a fully redundant notion for a topological manifold. But actually now we do something non-redundant, something non-trivial. We consider a topological manifold MO, and we call an atlas, or an atlas curly A, is called a flower atlas, if any two charts Ux and Vy, say, that lie in the atlas are flower compatible. So in other words, what we look at is that we have either the situation that the two chart regions U and V, which are open subsets in the manifold, do not intersect at all, then they're already flower compatible. Or if they have a non-zero intersection, then we require that if we map this intersection employing the chart map X to X of U intersected V, or alternatively employing the chart map Y that is defined on V, but then certainly also in the intersection Y UV, that if we consider this Y after X inverse chart transition map, so recall this is the chart transition map, then the observation already last time was that both X of U intersected V and Y of U intersected V, by virtue of the definition of a topological manifold, and indeed charts in an atlas, are subsets of Rd, where Rd D was the dimension of the manifold dim M we're looking at. So the chart transition map is not between manifolds in general, but between, it's a map from R dim M to R dim M. And now we know from last time that in a topological manifold, such a chart transition map is always a homomorphism, because X is a homomorphism, Y is a homomorphism, so the composition of X, Y and the inverse of X is a homomorphism, so they're always C0 compatible. But now we don't want the chart transition maps to be pairwise C0 compatible, but we want them to be flower compatible. So the requirement is that the chart transition map must be flower. Full stop. Okay, so before you think I finally turned nuts, what is flower? can be. So now there are various possibilities. Well, the simplest possibility is flower can be C0. So we had this before. We would say the chart, the atlas is C0 compatible. Well, it must be C0 as a map from RD to RD. We had this last time. Another possibility is that you require a different structure. The different structure another structure would be that it be CK. What does CK mean? Well, for manifolds, we're about to define what CK means, but we push this down as, to a condition on the transition map, and to be CK as a map from RD to RD means the transition map maps, all transition maps, are k times continuously differentiable as maps from RD to RD. That's the condition. That's CK. A manifold with such an atlas is then called a CK atlas, flower atlas, CK atlas, or it's a manifold with k times continuously differentiable transition functions. Another very often used, we'll see why, notion is C infinity, and that indeed means you can differentiate arbitrarily often. Okay, and such manifolds have a special name, or atlases. They're called smooth. And I'll argue in a second, after we define a few more things, that essentially, if the k is not 0, if the k is at least 1, then we don't need to make a big difference between CK and C infinity. We'll come to that in a second. Another used structure is C omega. Looks a little bit like an infinity, but it's an omega. And those are so-called analytic manifolds. And let's say, for instance, real analytic. That means the transition functions must be real analytic functions. And analytic functions are functions, roughly speaking, that can be Taylor expanded. So whenever your transition map can be Taylor expanded around every point of its domain, then it's called an analytic function. It's a stronger condition than C infinity. So every analytic function is C infinity, but not every C infinity function is analytic. And you certainly know examples from your analysis class for this. And yet another structure that's very heavily used is that we're talking about a complex manifold, so you call this a complex atlas, and then the transition functions now you wonder, so far we always mapped into some RD. How all of a sudden does this become complex? Well, there are different possibilities. I could go back, but we can keep this definition like we did so far, but then we have to take an even dimensional real manifold, and real even dimensional is a complex manifold if the transition functions, being continuous anyway, I must emphasize this, being continuous anyway, because otherwise they couldn't come from an atlas as we defined it, transition functions satisfy the Cauchy-Riemann equations. And you remember, so that's something like, well, you know the Cauchy-Riemann equations? You know that? No? Aha. Okay. Okay, look it up. So it's it's essentially, if you have a complex function of a complex variable, then you can write down the dependent variable, the x, not f of x, but it's complex valued. Okay, I write it down. I'm sorry. Okay, so say you have a function from R2 to R2. Now that's not complex, but we know that the complex plane as a set is isomorphic to R2, right? So now the question is, when can I call this a complex differentiable function? Now, if it is continuous already, and it satisfies the Cauchy-Riemann equations, which are those, well, I can write f of x plus iy, so the x is the one r, the y is the other one. I could write complex numbers as pairs, you know how that works. Then I can write this as u of x and y plus iv of x and y. So I decompose the dependent variable in real and imaginary part, and I decompose the result into real and imaginary part as a function of two real functions of two real variables. And then the Cauchy-Riemann equations are that du by dx is dv by dy, and du by dy is minus dv by dx. Now, a continuous function from R2 to R2 that satisfies the Cauchy-Riemann equations is as good as a differentiable complex function. And differentiability in the complex plane is a much stronger requirement than differentiability over the real numbers, because very roughly speaking, you can approach the limit point in so many different ways. Okay, and so that, of course, the field of mathematics that studies this is function theory, complex analysis, function theory, and the Cauchy-Riemann equations, if you have more variables, it's just you get indices here. So A, B, A, B, A, B, A, B. And then you have the Cauchy-Riemann equations for the transition maps. Okay? And you see, because you always have to split into two, that requires that dim M is even as a real manifold.
I think F is differentiable from C to C.
I'm sorry, yeah, thank you very much. Yeah, of course. R2 is the complex plane. Yes, thank you. Okay, so now you could add additional or a different structure, and you pick which one you want. Okay? And by far the most important one, for reasons I'll explain in a second, are the smooth differentiable structures and the complex ones. Okay? Right. So that's how we add structure. And now we have a theorem. This is, I think, Whitney. Any maximal Ck, but now very importantly, k greater or equal to 1. So this does not include k0, very important. Any maximal Ck atlas contains a C infinity atlas. Okay. And two Ck and two maximal Ck atlases that contain the same C infinity atlas are already identical. Okay. So, well, observation or implication. What does this mean? Well, it means once you found, say, a C1 atlas for a manifold, that already and two maximal that contain the same are already identical. Yes, so once you found a C1 atlas, it's not a bigger condition, it's not a stronger condition that you say the manifold is actually already C infinity, it's already smooth. If it's C1, it can also be made C infinity by removing more charts, right? So this is not the case. You could have a topological manifold where you do not find any differentiable atlas, okay? But once you're C1, you can go down all the way to C infinity. Okay, so therefore, it may sometimes be clever to say, well, this and that theorem is valid for C2 manifolds, but that automatically means it's for C3, C4, C5 anyway, because they're contained. But you can always construct from a C2 manifold, even from a C1 manifold, a smooth manifold. Okay, so if we talk about differentiable manifolds, or the existence of a differentiable structure, we do not need to distinguish between the different case, if you wish, because it goes all the way down. So do not need to really distinguish between CK for some k greater or equal to 1 and C infinity, so smooth, in the above sense. Okay, so that's the first remark. Now, what do we do with a differentiable structure? Well, first of all, we define the notion of a differentiable manifold with it, and then we can define what differentiable maps between two manifolds are. And that will lead us to the structure. These are the structure-preserving maps if they're also invertible, and that will give us a classification of smooth manifolds, and there will be the first surprises or very interesting points, even if you wish from the point of view of fundamental physics. But so, first of all, a smooth manifold, or a CK manifold. Let's be a CK manifold is a triple M, O, curly A, where MO is a topological manifold, of course that stays, and A is a maximal CK atlas. Okay. So we have this new additional layer of structure here, and I remind you, the CK atlas will always be a subset of a C0 atlas. So we take out strategically certain sets. Okay. Remark. A given topological manifold can carry different incompatible atlases. Now, I only define compatibility of charts, but it's pretty clear what I mean by an incompatible atlas. Well, technically, it's two atlases are compatible if their union is again an atlas of the same type. Or you could say you take two atlases, and if between any two maps between these atlases, you can have compatible maps of the compatibility type flower, then the atlases are compatible. But any given topological manifold can carry different incompatible atlases, and it's quite instructive to look at a very simple example. So for instance, we could consider as the underlying topological manifold the real line equipped with the standard topology, and then I could have atlas 1 consisting of only one chart, namely the chart where the entire R is covered, and the chart map X is the identity on R. We had this before. It covers, and it's a chart. It's trivially it's even a C infinity, it's C1, it's everything. Yeah, it's a C infinity atlas because, well, this chart overlaps with itself, but then, of course, the identity after the identity inverse is again the identity, and the identity is, of course, C infinity atlas. Now I take a second atlas that again consists of the entire real line, but now the chart map X is defined somewhat differently, namely where X, so that's the chart map, and it goes from, from R to R, and it maps a point A in R to a third root, A to the 1/3. Now, first thing to check is whether this is a chart map at all. Well, it goes from R to R. A, the third root, how does that look like? Like this? Fair? Okay. So this is clearly 1-to-1. It's also clearly continuous. It's also invertible, because that's clearly the third power. The inverse is also continuous, so it's a homeomorphism. Okay? As a map from R to R, but this is considered to be the manifold. This is the chart. This is R1, okay? So that's the logic here. This is a homeomorphism from the manifold R down into the chart. Okay? It's a chart map. That's fine. It's a perfectly fine chart map. And again, it has only one chart. This chart overlaps with itself. A third root after the inverse of that is again the identity. This is also a C infinity atlas. Now we can make both of them into maximal C infinity atlases by adding to this one all the other charts such that the transition functions are C infinity, and we can make this one A2 into a maximal C infinity atlas by adding all the other charts such that the transition functions between this chart and all the other charts is C infinity. But these two atlases are incompatible, because if I take their union, if they were compatible, I would be able to take their union and had another C infinity atlas. But that's not the case, because the transition map from here to here, A 1/3 after id inverse, say, is A to the 1/3. Well, this is still continuous, all right, it must be, but it's no longer it's no longer C infinity, because the derivative of the map at this point is infinity. That's not defined. Okay? So the point is that these two atlases, these two charts here, they are not C infinity compatible. Observe the chart R, id R, and the charts, and Rx, defined as down there, are not even C1 compatible. As long as they're parts of different atlases, that's not a problem, but I couldn't put them together into the same atlas and get a C infinity atlas. There would be an incompatibility. That means I can equip the real line with at least, well, this is just one example, with at least two different incompatible C infinity structures. Okay. Now this looks bad. This looks bad because it seems like I really have to make a decision which smooth structure I establish. We saw it's not so much of a choice that I have to do it for all the CK levels. That would be even worse. But essentially, I can worry about what the different smooth structures are. But even if I look at different smooth structures, this is far from unique for a given topological manifold. So if I want to do physics, and in physics we want differentiability, what a disaster this is. Not even the real line has a unique differentiable structure. Well, the situation is not so bad, but in order to explain this, I need the next definition. So definition. Well, but a given CK manifold is equipped with one specific choice of atlas. So here it's assumed I already made a pick. But which pick am I to make? Okay, before I can meaningfully talk about this, we have the next definition. Let phi from M to N be your map. Where, well, M and N suffices that they are sets in order to have a map. In order to have a continuous map, I need topological spaces, but now M and N are supposed to both be differentiable manifolds, where MOMAM and NONAN are CK manifolds. Then phi is called differentiable at the point P in M if. So you see, we now define the differentiability of a map. Could we define the differentiability of a map if we hadn't chosen a differentiable atlas, if we just had topological manifolds or topological spaces? No, we couldn't. There's no such notion. But so we're now going to use in an essential way the chosen atlas. I chose one. Which one? Doesn't matter. Chose one. And now we define the differentiability of this map by virtue of if, let me think, this is, if y, if, at the point P, if for some chart Ux that lies in the atlas for M, and where the U contains the point at which I want to check differentiability, if for some chart Ux in AM within and some chart V, Y that lies in the atlas of the target manifold, with V contains the image of the point P under the map phi. Why did I write F? Under the map phi. For this, with this, the map, I write it down here because I'll construct it in a second. The map Y after phi after X inverse is CK as a map from R to the dim M to R to the dim N. So why is this map a map? So from R dim M to R dim N. Well, very simply, I have the manifold M here, but I only look at the region U that contains the point of interest, and I have the manifold N here, but I only consider the region V where the image of this point lies under the map phi. And then I chose chart maps, well, these here, X, that bring me down to X of U. And from X of U, I go over here. I go down here with the chart map Y. I go to Y of V. And of course, because here we lie in a chart, this is part of R dim M. And this here is part of R dim N. And you see what happens. We actually want to talk about, so this is part of N. This is part of M. We actually want to talk about this object. We want to talk about the map from a manifold, differentiable manifold, into a differentiable manifold. But what we do, because we can, because we have an atlas available, the rule of the game is from the available atlases in the domain in the target, but only from the available atlases, pick a chart that covers the point of interest P and the image of that point under the map, and consider the map in its chart representation. That means look at the chart, look at that chart, and mimic this map up here by considering this path here, x inverse, then phi, then y. X inverse, then phi, then y. And consider this. Why? Well, because this is a map from R dim m to R dim n. And from Rm to Rn, we know what differentiability means. That's the idea. So we now define also the differentiability of this map by the differentiability of this chart representation of that map. Now that sounds all very good, but here I wrote if for some chart here and some chart in the target, this is true. Now, we need to worry about whether this notion of differentiability of the map up here depends on what charts I have chosen. What if I had chosen different charts around the point of interest and the target, the image of the point of interest, and had checked the differentiability there? Well, I need to show well definition of this notion. Proof that this lifting of the notion of differentiability from the chart representation of phi to the manifold level is well defined. Well, okay, now I wrote too much. This is very quickly seen. So we take U, V, those are the subsets of M and N, again, that contain the point P of interest and the image of the point P of interest with respect to the map I'm looking at. And we chose charts X to X of U and chart maps X and Y to Y of V in the respective atlases, so that's very important. And we considered, instead of the map phi, because about its differentiability we can say nothing, we need to pick U and V from the respective differentiable atlases, and we consider Y after phi after X inverse. That is what we had before, and we stipulated that this map be CK as a map from R dim M to R dim N, because that is where these respective sets lie. So far, so clear. Well, and by calling, if this is CK, we call this one CK. But now we would like to check whether if we had chosen different charts, and now we could be extra picky and say, well, the different chart has also a different chart domain. Instead of U, it has the domain U prime. Okay, but P must also lie in U prime, because that was one of the conditions. But then let's say U is already that intersection of the original U and the U prime, otherwise the picture gets messy. So without loss of generality, I have a different chart map X twiddle here that maps an open neighborhood of the point of interest into X twiddle of U, that of course again lies in R dim M. And I choose a different chart, V prime such that the intersection of V with V prime is non-empty, and then we call it V again. And I consider this map Y twiddle, so you have here Y twiddle of V being a part of R dim n. So totally unrelated map Y twiddle with respect to Y and X twiddle with respect to X. And now I can consider this map. And this map is, of course, now Y twiddle after phi after X twiddle inverse. And a priori, if this is CK, nothing guarantees me that this guy up here is also CK, so that I can conclude if it's true in one chart representation, it's true for all the others. Well, that would be bad, because then it wouldn't be well defined if that was true. But in fact, which map goes actually from here to there directly? Well, you can read it off here. It's the map Y twiddle after Y inverse. Everybody see that? Well, but what kind of map is this? Well, Vy and Vy twiddle are both charts, and the rule of the game was that these two charts had to be taken from the given CK atlas on N, right? But if these are two charts from the same CK atlas, then this is a chart transition map between two charts on that atlas. What do we know about, by definition, what do we know about the chart transition maps? Well, this guy is CK as a map from R dim n to R dim n. Now it's twice the same dimension because it's a chart transition map. Here dim m and dim n could differ because they're different manifolds. But now for the chart transition maps, of course, the same dim n. Aha! And what about this guy here? I can go directly from here to here by the very same argument, but now for the manifold M. This is X twiddle after X inverse. This is a chart transition map between two charts of the CK atlas on M. And now I see, aha, if I know, or if I checked, that this chart representation of this map phi between two manifolds at the point P, around the point P, is CK, then I can immediately conclude this is CK2, because I can write this up here as a composition of first this chart transition map, then this function, and then this chart transition map backwards. And because the composition of CK maps over Rn to Rm and so on is then again CK, that proves that once I checked it in one chart, it's true in any other chart. Very simple. But now we see why it was so important to restrict the charts I'm allowed to pick to be charts from a CK atlas. Because otherwise, this compatibility condition wouldn't be there. And if these were only C0, like they would be for any topological manifold, I could check CK here or right. But CK composed with C0 maps would possibly destroy the CK property and make this a merely continuous map up here. You need to be at least of the same differentiability class in your chart transition maps. Hence, on a CK manifold, you can define CK differentiability for maps between CK manifolds. You can define CK differentiability, but no higher differentiability than CK, because it might be destroyed if you want to check well-definedness, well-definition. Principle is clear. Philosophy, and this is the manifold philosophy. You want to define something for your object in the manifold, and you define it by looking at the representative of this in a chart or in several charts, because here you go from one manifold to the other, you need to pick two charts at least. But then you need to show it's independent of the choice of chart. And in order for well definition to work, you need to suitably restrict your transition functions. For instance, if you had complex manifolds and you wanted to check for complex differentiability, of course you could check all right in one representation, but if the chart transition maps didn't satisfy the higher dimensional Cauchy-Riemann equations, on top of being homeomorphic anyway, then you couldn't conclude that what you checked in one chart is true in any other chart representative. Hence, you couldn't attribute this as a property to the abstract object. Okay? That's the philosophy. And again, for topological manifolds, we didn't have to use the chart picture because we can define continuity in its own right between topological manifolds, for a map between topological manifolds, and pushing this into charts is redundant. But once we go beyond continuity, the chart picture becomes essential. In a sense, we steal from our knowledge of how differentiability works on Rn to Rm, we kind of import the notion, or we lift the notion to the manifold level. Okay? Now, definition. If this phi m to n is bijective as a map between sets, and both phi and its inverse, which then exists and goes from n to m, are C infinity, we could call it CK, but let's say C infinity, then phi is called a diffeomorphism. A diffeomorphism. So the diffeomorphisms are the isomorphisms, are the structure-preserving maps between differentiable manifolds or between smooth manifolds. Okay, and so then we have the next definition we already anticipated. Two smooth manifolds MOAM and NOAN are called diffeomorphic if there exists a diffeomorphism. You see, this is always the same pattern. There exists a diffeomorphism between them. Then we write M twiddle diff or C infinity or whatnot n. And you see, in principle, I should write the triple MOAM is diffeomorphic to the triple NOAN, because that's the full name of the smooth manifold, of the differentiable manifold. However, we now understood you have a set and you need a topological structure and on top a pick of a smooth atlas in order to talk about a smooth manifold. So in the future, I will lighten the notation somewhat and only mention the sets M and N, but if I say these M and NB smooth manifolds, you know that secretly they carry with them a choice of topology and a choice of atlas, and importantly, another differentiable manifold carries with it a naturally, possibly, different choice of topology and different choice of smooth atlas. So we'll now suppress this in a notation, but it shouldn't suppress this in your mind. It should always be there. We write this, and well, this is, if you wish, an equivalence relation, because M is diffeomorphic to itself, because the identity is a diffeomorphism, Okay, so, and we will not distinguish, or it's also custom to not distinguish between diffeomorphic manifolds. We call them the same. Seen through the glasses of differentiable structures, they're the same. Now, remark. It is custom to consider diffeomorphic manifolds, smooth manifolds, to be the same. But this is all a question of the level of structure. So you could have two sets. You could have two sets M and N that as sets are the same. Okay? There exists a bijection between them. Then you equip one with a topology and the other one with a topology. but unless there exists a homeomorphism between the extended structures, so they will not be homeomorphic. So you can have two sets that are the same, seen through the glasses of set theory, but once you add more structure, they're no longer the same, seen through the glasses of topology. But now you can push this on. But even if they're the same as topological space, if they're homeomorphic, you can equip them with different differentiable structures, and they're different as differentiable manifolds. We saw this before with the real line equipped with the standard topology. The real line equipped with the standard topology is the same as the real line equipped with the standard topology, trivially homeomorphic. So they're as topological spaces. But we can pick one smooth atlas for one and another smooth atlas for another one, and as differentiable manifolds, they're then no longer the same. Well, that's clear. So as soon as I start painting people's hair red and green, and then they're no longer the same. Okay. Good. So now it always depends on context when you say these manifolds are the same. So now we can go back, yeah?
I have a question. We had said that some sets are equal or isomorphic as a group structure.
Yes.
Where is the ranking?
Okay, it's somewhat, it's not necessarily a linear stacking. So, okay, thank you for the question. So let me, So, let's go back to base 1. So here we have a set. Now we can equip a set with a topology, and I need to modify my picture a little. So this is now equipped with a topology. But instead of equipping it with a topology, I could also equip it with some blob or some diamond, which is so set M, which is a map MM to M. And if this diamond satisfies certain properties like associativity, the existence of a neutral element in M, and the existence of inverse elements, then I call this a group. Now you can certainly, and I didn't close this here, because you could certainly equip a set with a topology and such a structure, and then you get a so-called topological group, or also called a Lie group. However, well, if you're on top, okay, let me refine this picture a little further. Okay, so on top of the topology, you can say it's a manifold, and then finally put there a differentiable structure. Differentiable structure. A differentiable manifold. So that is the path we went here, right? And as a side remark, we did this at some point, right? Okay. So now, once you're here, so once you've arrived here, so you have a set with a topology and a group structure, you have a so-called Lie group. Now, this continues if you stay over here. It was one of Hilbert's problems. You know this Hilbert around, I think, 1900, he gave a big speech. He said there are 22 problems that need to be solved in the 20th century, and da-da-da. And one of the problems was whether every topological group, called Lie group, is already a differentiable Lie group. And the answer is yes. Okay? So, and indeed, the analysis of Lie groups, topological groups, is best done by already employing some differentiable structure, and we will do so in this course. So we'll study Lie groups, and because the differentiable structure gives rise to the so-called Lie algebras, and by using Lie algebras you can study these Lie groups very efficiently, at least some aspects of it. Okay, anyway, so what this picture should confer to you is that you can have one structure and not the other, and but what you cannot have a differentiable structure without the thing being a topological space, and it can't be a topological space without being a set. But then you can combine these things in various ways. So another thing you could do, once you have here, okay, the picture gets even more elaborate. So let's say here, now you could also have okay, let's stick it out like here. You could have an additional structure like an S multiplication, And then you have this, and if they satisfy the right 8 axioms, then it's a vector space. Now you could equip a vector space. Oh my God, it gets complicated. You could equip it with a topology and so on. So you get the picture. You can combine the structures in almost arbitrary ways, but not completely arbitrary ways, because some structures require the other structure to underlie. And it's always very important. Do you talk about a vector space, or do you talk about a topological vector space? We'll come to that in a second. Okay? Yes.
Because I thought about the fundamental groups, and there we say they are group isomorphic to set or set Cartesian product
yes.
set. And my question was, could I say because they are not isomorphic in the topological sense, the torus and the cylinder, then I could also say they can be isomorphic in a group sense?
No. Because this is talking about the same set is being equipped with more and more structure of this and that type and that combination. If you look at the topological manifold as we did, so you're somewhere here, and you identify the fundamental group, then that is constructed from the topology. Yes, constructed from the topology, you construct a group which, however, has its own underlying set. So remember the torus, which had the underlying set integers, Cartesian product with integers, Z cross C, but that's then a different set which carries a group structure and so on. So it doesn't mean that in one mathematics problem things have to always come in this structure. You can construct from one, you can construct a group based on a different set, and then you have another building like this, and so on. Okay. It looks pretty. Maybe it's more confusing than enlightening, but I wanted to say that it's not like every structure has its exact place in one such linear stacking here. I mean, that is not what I wanted to convey in my original drawing in the first lecture. Okay? Good. So now that we have the notion of differentiable manifolds to be essentially the same, we can return to this question: how many differentiable structures are there up to isomorphism? So the question is before, so now return to question, now return to the question of whether, for instance, we consider the real line equipped with the standard topology, but we equip it with the maximization, so the extension of this atlas 1 we constructed for the real line. You remember the previous example? And we can now ask the question whether this is maybe at least diffeomorphic to the real line equipped with the standard topology and equipped with the atlas A2, or rather its maximal extension. So you see, they were clearly not the same, because this atlas A1 max and the atlas A2 max, they were different. Okay? We constructed only one chart in each atlas, but once you have one chart, you can add all the other charts that are compatible with it, and you get the maximization of that atlas. Clearly, these two were different, and we started worrying. We said, well, I mean, if that's possible, which structure on the real line would I use as the differentiable structure? Okay? But we shouldn't be so precise and look only at the atlas. We should worry whether the resulting differentiable manifold differs in an essential way from the other one. An essential differing in a non-essential way would be if they're diffeomorphic. Then we'd say, well, then they are the same from the point of view of differentiability, because every function that's differentiable on here can be pushed over here and would be differentiable and so on. Okay? So we can now revisit this question, and there are the following results, which are, however, rather deep results. We're not going to prove them, and some of these results are real big achievements. So we can now ask the question, how many differentiable structures, how many differentiable structures, how many different differentiable structures can one can one put on a given topological manifold? So the idea is I hand you a topological manifold and you have to decide which differentiable structure do I put on it, and the whole thing is up to diffeomorphism. And the results are quite surprising. So the answer is depends on the dimension. Depends on the dimension of the manifold. So dimension M equals 1, 2, or 3 is one class. So up to 3-dimensional manifolds, everything is fine. So this is Radon-Moyse theorems. They say that there is essentially only one differentiable structure. Well, there are several differentiable structures, but all these manifolds are diffeomorphic. Okay? Up to diffeos, all there is a unique differentiable manifold. And I should say a unique smooth manifold. Smooth manifold one can make of a given topological manifold. That's nice. So although we had this issue that we could choose different smooth charts already for the real line, it doesn't matter. The atlases are not compatible, but the resulting manifolds, they're at least diffeomorphic, so we don't worry. That's great. So everything you do with differentiability is unique. Even if you put it on a manifold, you can now have now a notion of differentiability on the torus, say. I mean, see what an achievement this is, right? So where's this? In high school, you learn how to do differentiable calculus of one variable over the real line. Then you go to university and you take an engineering course and you do it over Rn or R3, let's say, and so on, and you continue. But now you can do it on arbitrary manifolds. There are holes in it and whatnot. Okay? But up to dimension 3, everything is unique. So that's A. Now B is, well, let's go to, let's leave out 4 dimensions. Let's take dimension of M is greater than 4, but not 4. Decidedly not 4. So, I mean, the symbol says it all, but I emphasize it. Decidedly not 4. Then there is a technique, a toolbox that's called surgery theory. And surgery theory is really what it says. You take, say, a sphere, and you operate it like a surgeon. So you take your scalpel and you cut out some piece of it, and say you also take a scalpel and cut out some piece. Now your colleague comes and gives you the new heart, but here it's not a heart, but say the colleague comes and gives you a cylinder, and you push the cylinder in here, and then you sew it here and you sew it here, and then of course what you get is the torus. Isn't that right? So you perform surgery on a sphere. Again, I don't know what the gender theorists say to this, but you have a sphere and you have a, okay. You perform surgery. Okay. And the idea, I mean, this is a big field. The idea is you understand the sphere pretty well. You understand the cylinder very well. And now if you perform surgery in such a way that you control topological invariants you care about, like, say, the homotopy group, the what's it called, the fundamental group and stuff like this, and later on we'll talk about homology, then you can understand the torus by performing surgery. But that's, of course, only a very trivial example. The idea is to understand all the manifolds in higher dimensions, higher than 4, by reducing them to elements and suing surgery procedures you understand. And by doing this in a systematic way, I think it was in the 60s, this has been done, in the 1960s, people showed that for dimension dim m greater or equal to 4, there are only finitely many. There are only finitely many different smooth manifolds one can make from a topological manifold, from a given topological manifold, but the dimension needs to be greater than 4. Okay, so that's not so neat like dimensions 1, 2, 3, but at least they're finitely many, so you have a chance in principle to enumerate them, to write them all down. So you say, let's take the 4 sphere, okay, and let's try to find all the differentiable structures. Well, if you really want to do this in practice for a given manifold, it may be very difficult to do that, to find all of these, but the theorem says they're only finitely many. So imagine, like some physicists believe, that the world is, say, 10, the space-time is 10-dimensional, and okay, not proposing nor condemning that, but if that is the case, then you need to worry which smooth structure you equip this manifold with. You can say, yeah, okay, physics can make experiments. If these different structures lead to different results, different observations, we can at least enumerate them and make finitely many observations and distinguish between all of them, in principle, okay? So this situation is not so bad. So if the world is higher dimensional, if the space-time is higher dimensional, that's in a sense good news, because you could probably, I mean, not probably, in principle, you could maybe determine by experiment, if you apply this to physics, by experiment, which of these structures nature has chosen, if any, if space-time is a differentiable manifold in the first place. But you see the point. This has direct impact to fundamental physics that these are finitely many. You can say, oh, this is very abstract mathematics. It has immediate impact on physics if you take it seriously. And we want to do that. Okay, so now see the special case, the dimension is 4. So I hand you a 4-dimensional smooth manifold, like R4. And I ask you how many different, up to diffeomorphism, smooth manifolds can you construct from this? And the answer is non-countably many. Different smooth manifolds can be made of the same 4-dimensional topological manifold, in particular R4, equipped with the standard topology. We know this is a topological manifold of dimension 4. And you have non-countably many different ones. This is at least true for non-compact, for the non-compact case. So here we can have C.1 is the non-compact case, and C.2 would be the compact case. Okay. And in the compact case, at least compact case, they're only partial results, okay? Partial results. If the so-called Betti number, there are several Betti numbers, this is the Betti number B2, that's a topological invariant, is greater than 18. What's the Betti number? Very roughly speaking, the first Betti number, Betti numbers, They're actually defined in terms of homology groups, but intuitively, the zeroth Betti number is the number of connected pieces your space has. The first Betti number is the number of circular holes, or one-dimensional holes, and B2 is the number of two-dimensional holes. And that continues. And if the number of two-dimensional holes, like say the pretzel, but with 19 holes or so, okay, the Betti number is greater than 18, then you can show there are only countably many. Countably, infinitely many, different, smooth, manifolds. But you see, okay, compact would probably not be space, but anyway, it's still infinitely many. So it's not much better. But the compact case is a little better than the non-compact case. But so when Einstein says space-time is an R4 equipped with some additional structure, namely the light cone structure or the metrics, more specifically, or more specially, which is special relativity, and you derive, you find the tangent vector to your world lines, I mean special relativity. The question is, which smooth structure do you put on this R4 as a topological manifold in order to do special relativity? You have non-countably many you could choose. Can you do experiments to distinguish between them? Well, you would need to, if you're lucky, you need non-countably many experiments to distinguish or to find the one. It's not so good, right? But it's a result. Okay. So unfortunately, I have nothing better to say about this, but it's just an observation, and this is what the analysis yields. Okay. So maybe, well, it's serious. I mean, from a philosophical point of view, this is serious. I don't know whether from a scientific, practical point of view it's serious, but in principle our theories could fail if we do it on R4. They could fail maybe because we chose the wrong differentiable structure. And maybe it could be repaired by choosing another one. Okay, I don't think this is a point where you could start doing research, but maybe you can, I don't know. But as a mathematical result, it stays and should be noted. So all right, so we define a differentiable structure, and the question is, so what? We have a structure we can classify, but what we really want, and what is really new about differentiable manifolds, is that, roughly speaking, they have tangent spaces. We can now meaningfully talk about tangent spaces. So the key feature of a differentiable manifold there exists a tangent space, and I put this in quotation marks because you may have an idea of what a tangent space may look like, but that idea we will actually not use. Well, but we'll go about this in a different way. Exists a tangent space at each point of the manifold. So the intuition to this is the following. Say you have a sphere. Now, if we look at the sphere as a topological manifold S2, we intuitively always think about the sphere as being embedded in the three-dimensional space. But of course, as a topological manifold, it doesn't care about whether it's embedded in a three-dimensional space or not. It simply doesn't care. We say it's the topology as a manifold, it's intrinsically defined. You have a set that is equipped with a topology, and neither the set points nor the topology make any reference to what lies outside the surface of the sphere. Okay. Now, the same stays true if I start equipping the sphere additionally with a smooth atlas, say. it's still this thing by itself. Again, we can think of it as being embedded in R3, okay? But actually, it's an object that doesn't depend on the embedding. Now, if I explain tangent spaces in the following way, then I say I take one point of the sphere, and for dramatic purposes, I rotate the point such that it's here on the horizon for you. And then I say the tangent space I imagine to be all those points or vectors or whatnot that lie in the tangent plane. You immediately get the feeling, well, hang on, this now starts making reference to the space into which this is embedded. Because this tangent plane, as it's drawn here, is a part of the space in which I think this thing to be embedded, but which has nothing to do with the smooth structure, because that is quite independent of the embedding, okay? And indeed, this is not the way we are going to define these tangent spaces. We're not going to define them as being planes in some exterior space in which the smooth manifold is embedded. We're not going to do this. Well, due to various theorems that have been proven, one could do it this way without loss of generality. Okay? Nevertheless, we're not going to do it, because now imagine this is not two-dimensional, but it's four-dimensional, and it presents our universe. So we want to talk about space-time. And then we are going to construct a notion, and if the space-time is supposed to comprehend the entire universe, to model the entire universe, it would be kind of a little bit funny to think of the universe being embedded, physically speaking now, being embedded in even a bigger space in which then the tangent spaces lie, because then that bigger space would obviously be what we should call the universe, the thing that comprehends everything. Okay. So even from a physical point of view, not purely an aesthetic point of view in mathematics, but also an aesthetic point of view from theory building in physics, it's nice to construct everything intrinsically, that means without taking recourse to structures that lie outside the actual object. So we need to come up with an idea to define these tangent spaces solely using the structure we are handed, notwithstanding our intuition. You may think of tangent spaces this way, but it's better not to define them this way. Okay, that's the first remark. So now, in the following few subsections, we will fix a point on the manifold, and we'll start constructing the tangent space at this point, the dual to this tangent space, and even the tensor spaces over this point. That's the first thing. And then there will be a couple of subsections later where we're actually looking at all the tangent spaces together. And if we can talk about vectors, tangent vectors at one point, they will constitute a vector space. But if we look at all the points together, the whole thing will constitute a vector field on the manifold, because at every point I can look at a different vector. Okay. Now, you know the mathematics of vector spaces. Now, that's linear algebra, like you probably took a course in linear algebra, and we'll quickly review some linear algebra notions, in particular the construction of tensors and so on, because there's some standard confusions that we will now try to eliminate once and for all. Now, however, if you continue to consider vector fields, vectors everywhere, you still have a linear structure on vector fields, because you can add to vector fields, but you can also scale a vector field. But at different points of the manifold, you could scale it differently. You could scale it with a function. And it turns out that the strict notion of a vector space is no longer, is too restrictive to also deal in a clever way with vector fields. And we go to another type of structure that's called a module. Who of you saw modules in linear algebra? Oh, fantastic. Okay, good, very good. So that will be new for you, but then it's my responsibility. All your future misconceptions will be my responsibility then. Anyway, and so this is also, I think normally if you study mathematics, it's linear algebra 2, you consider modules. Very useful structure. And again, we'll see also in physics, we use them all the time. We just choose to ignore that they're not really vector spaces anymore.